Hello Professor, my name is Taowen. Thanks for your time for watching this video. In this presentation, firstly, I would like to introduce my background. Next, I will briefly summarize my research works. At the end, I would like to introduce my research proposal. I obtained my bachelor degree in Lanzhou University and my doctoral degree in the Institute of Chemistry, Chinese Academy of Science. Then I spent 1 year in the University of Freiburg as a postdoc fellow. Currently, I'm a postdoc fellow in the National Tsinghua University. For materials, the final performance does not depend only on their chemical structures, but also on how they are organized across different length scales. So to achieve a material with design function, we need to control not only their primary chemical structures, but also the hierarchical structures at different levels. To make accurate translation of molecules to final materials, it is important to consider the physical interactions that dominate at the length scales beyond that of molecules, such as intra- and intermolecular interactions and interfacial and surfacial interactions. My research work focused on the controlling of self-assembling of Bloch polymers and the crystallization of semi-crystalline polymers by using chemical and physical concepts, such as molecular designing, chiral doping, and surface inducement. In the first part, I would like to introduce the controlled self-assembly of chiral Bloch polymers by molecular designing. Bloch polymers self-assemble into different ordered structures. In our previous study, a unique nanostructure named as helical phase was found in the self-assembling of chiral Bloch polymers. Compared to the cylinder phase formed by a chiral Bloch polymer, the formation of helical phase reflects the chirality transfer from chiral block to self-assembling the nanostructures. In this process, the chiral information can be transferred from chirosynth to polymer chains through interchain interactions, and then from helical chains to asymmetric structures through intra-chain interactions. In this study, we are supposed to control such chiral effect in self-assembly. We designed and synthesized polystyrene polylactide tri-Bloch polymers, including both of chiral and a-chiral blocks. By tailoring the sequence and the length of the chiral and the a-chiral blocks, we can control the chiral effect in self-assembly. For Bloch polymers containing a chiral middle block, the helical phase can always be observed. However, for Bloch polymer with an a-chiral middle block, the situation is more complex. The final morphology can either be helical phase or cylinder phase, and it depends on the length of the middle block. We speculate this is because the self-assembly of chiral Bloch polymer is determined by the chirality transfer from chiral block to the interface of macrophase domains. For Bloch polymer with a chiral middle block, the interface is also chiral. In this case, the helical steric hadrons and the interface can directly induce the formation of helical phase. For Bloch polymer with a chiral middle block, the interface is also a-chiral, and in this case, the final morphology depends on whether the chiral effect can be transferred from chiral block to the interface or not. If there is a short a-chiral middle block, then the chiral interactions can be transferred from chiral block to the interface and result in a curved interface, which means helical phase. And if there is a long a-chiral middle block, the chiral interaction will be blocked by a-chiral segments, so we will have a straight interface, which means cylinder phase. This work demonstrates the importance of interfacial properties in self-assembling of Bloch polymers. Inspired by this work, we started to study the impact of junction interactions in self-assembling of Bloch polymers. We synthesized 3 polystyrene polylactide Bloch polymers with different junction structures. The first one is Bloch polymer with an aliphatic junction, and the others are broken polymers with aromatic junctions, naphthalene and pyrrole. The idea is that the pipette interaction between aromatic junctions will compete with the microphase separation of broken polymers. Based on morphological observation and X-ray scattering, we found that the structural ordering of self-assembling is determined by such competitive interactions. For broken polymer with a high molecular weight or weak junction interactions, all the structure can be observed. That means, in this case, the microphase separation is the dominating factor of self-assembly. However, for broken polymers with small molecular weight or strong junction interactions, the degradation of all the structure can be clearly observed. This is because as the junction interaction is stronger than the segregation strength of broken polymer, the junction stacking will be the dominating factor in self-assembling, and the formation of junction stacking will destroy the microphase separation of broken polymers. Those results indicate the junction effect on the self-assembling of broken polymers. Interestingly, the structural ordering of broken polymer with aromatic junction is correlated to their optical activities. Let's take broken polymer with naphthalene junction as an example. For broken polymer with high molecular weight, there is no Avoid Cotton effect can be observed, and the absorbance wavelength of junction molecules. This is because all the structure can be achieved in this broken polymer due to strong segregation strengths. In this case, the junctions are forced to locate at the interface of microphase domains. Because those chromophores are well separated to each other, so it will show CD silent. However, for broken polymer with small molecular weight, junction stacking is a dominating factor and result in a disordered structure. For one thing, the junctions are closely packed to each other by strong pipette interactions. Another thing, the junction stacking could have an exclusively one-handed twisting fails due to the inducement of connected chiral blocks, in this case, non-racemic polylactide. This is also a chirality transfer process. As a result, the induced Cotton effect can be generated by such helical stacking of chromophores. Because the states of junction aggregation can be easily detected by CD spectrum, so it allows us to deduce the degree of structure ordering from the result of CD detection. These results provide a new thread to study the nanostructure of broken polymer in thin film. In the next part, I would like to introduce the controlled handedness of twist lamella in banded spherulite. Banded spherulite is a common morphological feature of polymers. For polymers with optical activity, the handedness of twist lamella in banded spherulite is controlled by the chirality of polymer chains. That means the twist lamella in banded spherulite will have exclusive handedness, which depends on the chirality of the polymer. By contrast, for banded spherulite polymers without optical activity, the population of right-handed and left-handed lamellae are equal. In this study, we use isotactic poly-to-vinyl pyridine (IP2VP) as model system. The pyridine rings of IP2VP can interact with chiral acid through intermolecular interaction, and then the chiral information can be transferred from chiral dopants to polymer chains. This process is known as induced circular dichroism, or ICD. By means of ICD, the helical conformation of IP2VP can be controlled. For instance, if the chiral dopant is R-type, then the chain conformation will be right-handed. If the chiral dopant is S-type, the chain conformation of IP2VP will be left-handed. Banded spherulite of IP2VP can be prepared by isothermal crystallization of IP2VP with chiral dopants. For IP2VP crystallized with R-type chiral-doping, the twist lamellae are right-handed. And for IP2VP crystallized with S-type chiral-doping, the twist lamellae are left-handed. The corresponding CT spectrum also confirms this result. It is proved that the handedness of twist lamellae can be controlled by the presence of chiral-dopants. In this study, we start up with all-chiral polymers with flexible chains. The helical conformation of polymers can be controlled by ICD, and the packing of polymers with certain helical conformation can give rise to twist lamellae with preferred handedness. In this process, chiral information is transferred from chiral dopants to polymer chains and to twist lamellae. It's an example of homochiral evolution from molecular level to hierarchical level. By summarizing our recent works, we developed a methodology to determine chirality and different length scales. For molecular chirality, it can be detected by electronic CT spectrum, and for conformational chirality, it can be detected by vibrational CT spectrum. For nanostructures assembled by Brocken polymer, for example, helical phase, the absolute handedness of the structure can be mirrored by TEM tomography, and for the twist lamellae of band-through light, it can be detected by light microscopy. Next, I would like to introduce the morphological controlling of semi-crystalline Brocken polymers by surface inducement. Here what we used is olefin Brocken polymer, which was developed by the Dow Chemical Company. There are two different blocks in this Brocken polymer, and phase separation will take place at the male state. Final morphology of the thin film is determined by the strength of surface inducement. If there is a weak surface inducement, crystallization will be confined within the phase domains. And if there is a strong surface inducement, induced crystallization can break through the phase boundaries and form continuous network. The strength of surface inducement is determined by the degree of matching between surface structures and crystal structures. Also, we developed a method to mirror the nucleation capability of one polymeric material to another. Based on our result, we proved that there is no existential relationship between polylactide home crystals and its steric complex. In the last part, I would like to introduce order transition of Brocken polymers studied by TEM tomography. We know that TEM is a powerful tool to study nanoworld. However, one limitation of TEM is that it only provides a two-dimensional projection of a three-dimensional object. TEM tomography is a technique that allows us to achieve three-dimensional structures from a series of two-dimensional images. In this study, the phase transition of double geoid structure under confinement was studied by TEM tomography. We found that the thin film of geoid structure could transfer to a unique double-layer HPL structure after long-time thermal annealing. The result of three-dimensional observation clearly indicates the morphological evolution of PDMS framework under thermal treatment. This study provided a new insight for the order phase transition under spatial confinement. As a short summary, my research work studied on the self-assembling of Brocken polymers and the crystallization of semi-crystalline polymers. By using chemical and physical approaches, we carefully regulated the intramolecular interactions, intermolecular interactions, and spheral interactions to control the translation of molecular structures into the hierarchical structures at different scales. In particular, the chirality transfer can be controlled either by intrinsic chemical structures or by chiral inducement through intermolecular interactions. it provides a possible concept for the development of materials with optical activities. In addition, the application of TEM tomography allows us to achieve a deep understanding for phase transitions of complex morphologies. Finally, I would like to introduce my research proposal for future works. My future research will be focused on the development of hybrid polymeric materials and their applications for energy storage and nanopatterning. There are two important questions I asked to myself: why I choose hybrid materials and how to do that. Hybrid materials could provide a unique platform for developing advanced materials, which could combine the advantages of polymeric components and inorganic components. We know that hybrid materials had been successfully applied in many fundamental areas such as coating and optical devices. To promote innovation of hybrid materials to the cutting edge of industry area, three key issues will be carried in my future work. Precision synthesis will control hierarchical structures and effective post-processing. There are three study objectives in my future research. First one is the development of hybrid Vulcan polymers for solid electrolyte of secondary batteries. In this study, we will develop hybrid Vulcan polymers for the solid polymer electrolyte of lithium batteries and proton exchange membranes of fuel cells. Besides the active blocks, the nature of Vulcan polymers provide a network structures with tunable morphologies. Also, inorganic building blocks can be designed as cross-linkable junctions or multifunction sites. As a result, the combination of Vulcan polymer and hybrid components can give us a large space and opportunity to develop electrolyte with outstanding performance. The second objective is to develop the application of TEM tomography on the study of morphological evolution of polymeric electrolyte under circuits. The motivation of this study is the fact that the decay of performance and the lifetime of battery strongly depends on the structure falling during repeat circuits. We believed that the three-dimensional visualization can provide a better understanding on the structure-performance relations of electrolytes, which can also lead us to design and control the hybrid Vulcan polymers mentioned before. In particular, our attention will be paid on the interface between electrolyte and electrode, because the high reactivity of the electrode surface and the intrinsic instability of electrolyte components. The third study objective is surface nanopatterning by hybrid giant molecules. Hybrid giant molecules refers to the molecules constructed by organic and inorganic nanobuilding blocks. In this study, we will mainly focus on the hybrid giant molecules containing polyhedral oligomeric such as queen oxide or POS building blocks. Compared to the Vulcan polymer, hybrid giant molecules have several advantages in nanopatterning, such as smaller feature size and a higher long-range ordering. This work will mainly focus on the fabrication of sub-10 nanometer nanopatterning by self-assembling of hybrid giant molecules and its potential application in IT industry. Finally, I would like to thank all of my advisors and my colleagues. Thank you very much.